This is Node3. We are continuing from dispatch B, January 2022, the 25th. This is a continuation right before Schrodinger's cat is explained. And again, this is from the Perimeter Institute in Canada.
We have very firm confidence that the formulas of quantum mechanics describes that situation, and the way it describes it is by associating something called a wave function or probability amplitude with each of these two paths. And then the important point of amplitudes is that they can be positive or negative. Actually, more complicated than that, but for our purposes, they can be positive or negative. So you can get, for example, the positive amplitude coming through this path, a negative one coming through this path. The total amplitude then to get there will be zero. And that's the way we're explaining this phenomenon. Now, so we've got a lot of confidence that the formulas of quantum mechanics works at that kind of level. But now if we believe that everyday matter, tables, Geiger counters, cats, etc., are made up of atoms and electrons and so forth, then they too should obey, at first sight, the laws of quantum mechanics. And then it turns out, and this was a point made by Schrödinger in a very famous paper more than 70 years ago, it turns out actually engineer a situation where if you believe quantum mechanics, the appropriate description of the world is that you have a probability amplitude for a cat. So you have a cat inside a closed box and you engineer things that at a particular time there's a probability amplitude, non-zero, for her to be dead, and a probability amplitude for her to be alive. And then the question is, how do you interpret that? I mean, at the microscopic level, whenever you had this kind of situation, you could not say that each atom went through one way or the other. In this case, can you say each cat is definitely alive or dead at this stage? And this is where perhaps the most furious argument in the whole of the foundations of physics breaks out. People disagree furiously about whether you're allowed to say each individual cat is alive or dead. And I personally believe that if you really take quantum mechanics seriously and you consistently interpret it in the same way at this level as you did at the level of atoms, then you can't.
No, why is that significant? Why is that important?
Well, because, I mean, look, the Animal Protection Society is very lucky to have invented us from doing this experimental statistically way. Very few of us doubt that we were to do it. And we had a whole box of 100 cats, 100 boxes each containing the appropriate cat, and we set this up properly. Then I think all of us believe that whenever we took the lid off box number 97, that particular cat would very definitely be either dead or alive. In fact, we'd like even to see her in an indeterminate state. So, in other words, we have very, very difficulty in reconciling the interpretation of the quantum formalism, which we're used to giving at the microscopic level, with our sort of common sense experience at the macroscopic level, everyday level.
Okay, so in other words, because you can't look in the box, at the time when you don't know, the cat could be either alive or dead, and you're calling that's itself a sort of a state of being.
Well,
it could be both.
It's not that it could be either alive or dead. It is, in some sense, neither alive nor dead. Just as the atom is not true to say that the atom went through one path or the other.
Okay.
There's nothing particularly unusual about the idea that there's a box in which a cat may be either alive or dead.
No, absolutely not.
So this is not the whole story. The whole story has something to do with, as you know better than anybody, with something called coherence. And roughly speaking, I would say what's implied here is that you can do something called an interference experiment, which, and it's very hard to describe, but I think one could say, oh boy, I don't know how to describe that. Maybe give it a shot, but you have not said the whole thing when you just said there's a box that can have a cat, which is either alive or dead.
No, but can I take up on that? Yeah. indeed, the phenomenon of interference is fundamental. How do we know at the atomic level that it is not true that an atom went through one path or the other? Because precisely of that phenomenon of interference, which in the simple example I gave, said that get a finite number coming on one path, a finite coming by another path. When both paths are open, nothing. That's a particular example of destructive interference.
But what I want to get at though is how does this uncertainty or this dual existence possibility have to do with information, which is what we're really talking about tonight?
Oh, well, okay, I think I would turn that over perhaps to, for example, Chris.
You won the Nobel Prize.
He's smart. Knows when to quit.
Also demonstrate why I'll never get a Nobel Prize.
I mean, if I were to give you my resolution of the problem, it would be strongly heretical. One which I suspect none of my three colleagues here tonight really share, which is that I think that the whole of the Schrodinger's cat paradox rests on an implicit assumption, which is a very, very natural implicit assumption. It's one we make unthinkingly every day of our lives, practically, and it's this. If you have a theory, I mean, big things are made of little things, pretty speaking, okay? So if you have a theory which describes excellently the behaviour of little things, then it should describe excellently, at least in principle, the behaviour of the big things made of them. That may not be true. That would be my solution to the problem. A solution perhaps ought to come in points, but
Okay.
but I say that's heretical. It's very heretical.
Okay. So, folks, how do you relate this to information?
Sure, for a completely different answer. So there's this mathematics called quantum mechanics. I mean, there's a physical theory, and it has mathematical terms in it. And among those mathematical terms is one called the quantum state. People talk about the quantum states of things. And for instance, Tony was talking about the quantum state of a cat. One possible quantum state for the cat is alive. Another possible quantum state for a cat is dead. And when one has this paradoxical issue with the cat in the box, one writes down a new quantum state that is alive plus dead. And the issue is, what the hell is that? Now, if one thinks of quantum states as states of reality, in other words, when you write down this thing called alive, it means the cat is alive. I mean, and the cat's alive regardless of me. And if you write down dead, it's dead. It's dead regardless of me. If you think that those mathematical terms correspond to properties of the cat, that it can be alive or that it can be dead, you run into troubles. Where information comes in is with the realization, at least for the belief of some physicists, that these mathematical objects don't represent states of reality, but represent states of information. So when one writes down alive, it means, oh, I can predict that when I open the door, I see the thing alive. If one writes down dead, it means, I predict that when I open the door, I see it dead. And when one writes down alive plus dead, one is predicting still something else. One is predicting if you open the door and look to see whether it's alive or dead, you'll get that answer. But you can also predict that you would see other things called interference, like Professor Susskind was talking about, with more complicated apparatuses, not just our eyes and opening a shutter, but you surround the box with some interesting equipment like Seth Lloyd is talking about, a big quantum computer, and you can see these other things. And that's where information comes in.
The ironic thing is that indeed we are now doing experiments building quantum computers using superconducting circuits, using an idea that Tony, that you proposed, that's what is called macroscopic quantum coherence, in which a zero is represented by a gajillion electrons going around a superconducting loop this way, and a 1 is represented by the same gajillion electrons going around the loop this way. And we can, with some difficulty, but not that much difficulty now, create a state of these gajillion electrons where they're going around both ways at once. So they're effectively instantiating this Schrodinger's cat.
And you can not only create it, but actually verify, crudely speaking, that's what you've got, right?
Right, exactly. You can demonstrate exactly the kind of interference that Leonard was asking us to demonstrate. And in fact, do things like quantum computations, do funky algorithms, take several of these things, entangle them together. So it's interesting. I guess the question is, you were suggesting that maybe macroscopic things don't behave in the same way, but now we have things that are more and more macroscopic, actually following up on your own suggestion, right? Demonstrating experimentally your own suggestion, things that are more and more macroscopic that are being dead and alive at the same time.
But if you're saying that, the little things, as you say, and the physics there don't match the physics of the big things, then what about this whole effort to try to come up with this grand unification theory that brings everything all together, if what you're saying is right? Doesn't it prevent that from happening?
I think in the usual technical sense of grand unification, it wouldn't have any major impact there, because you're, as I understand it at least, you are dealing there with attempts to unify different theories of elementary particles. You're only talking about, in some sense, a rather few elementary particles at a time. However, it would have very substantial, if what I said does turn out to be right at some stage, then it would have very substantial impact on certain ideas about applying quantum mechanics to the universe as a whole.
Yeah, let me try to say it a slightly different way. There's a thing called the uncertainty principle about particles. In principle, it should apply not to just the single, small, tiny elementary particles, but to baseballs and everything else. Now, it's very hard to test. But if you had a baseball, because of the uncertainty principle, there's certain limits on predictability, and in particular, those limits on predictability follow from quantum mechanics. If you believe that quantum mechanics applies to baseballs, if you believe that you can use the rules of quantum mechanics as the standard quantum mechanics requires, I think Tony would say, quantum mechanics possibly may really break down. The rules may really break down for studying baseballs, and that's an experimental thing that can be tested, and it has never ever been tested for large systems. Quantum mechanics has never been tested for objects bigger than, I'm not sure how big, but I'm not sure what the largest system that's ever been, it's been tested for. And so it's perfectly appropriate. It's a really mainstream question. Will the rules of quantum mechanics apply when applied to objects much bigger than it's been applied to now? And nobody knows the answer. But what I would say is I think there's some circumstantial evidence that it would. And the circumstantial evidence is that it's very hard to isolate breakdowns of quantum mechanics. You say in looking at grand unification theories that you're looking at very small number of particles. But in fact, those small particles contain virtual particles, and the virtual particles contain other virtual particles, and eventually you're talking about a lot of particles of very small size and very heavy mass. And the fact that quantum mechanics applies to that is some kind of indirect evidence that it might apply even to complex systems. Now, I would be the first to admit that's a weak argument, but a weak argument in the sense you better go and test it directly anyway.
Okay, I want to get on to a topic that I'm interested in, which is one of the weirdness aspects of the quantum world. Dr. Lloyd, tell me about teleportation.
Oh, teleportation? You mean as in beam me up, Scott?
Well, whatever your definition of it is.
Yeah, so there was a book, I might be out of print, called The Physics of Star Trek.
By Dr. Lawrence Krauss.
That's right, by Larry Krauss. And in the original version of this book, he investigated the possibility of performing teleportation. Can I step into a little booth here, be dematerialized, the bits of information that get measured here are sent somewhere else, and then I'm rematerialized over there. Actually, it looks like I got rematerialized in a left-handed universe from a right-handed to left-handed here.
Either that or a fly.
Well, I mean, yes, the other thing, of course, like the other thing that typically happens is the process goes awry, and you're left with, the good Kirk and the evil Kirk, and somehow they have to be merged. That's also, it's kind of Schrodinger's cat-like, actually, now that I think about it. So, now, Larry Krauss pointed out that.
Someone's not doing their job. Okay, let's keep Shopping for the game can be a minefield for young homeowners who have turned into their parents.
Can you believe how many different types of water they have in this aisle? Kim, did you just change blades back there? This is perfect. Jackpot, variety pack.
Remember, it's a football game, not a play day.
Roger that. One more slice.
It can be a lot.
Oh, good, the manager. Brian and produce, very helpful.
Progressive can't save you from becoming your parents, but we can save you money when you're flooding low on with us.
Pulls to the left a little bit.
Now, Larry Krauss pointed out that really you couldn't do this because if what you imagine just taking a measurement and you measure the state of this system right here, you can get a lot of bits. You know, for a typical human being, you'd get something like 10 to the 30 bits out of this human being. That's about how many bits are required to describe a human being. But you would at the same time destroy the state of this human being, and you would not learn all sorts of features about its state, because quantum mechanical measurement on its own is both destructive and incomplete. You can't tell everything about the system. And so that says, well, you shouldn't volunteer to go through a teleportation experiment, because when you come out, you will be quite different from when you went in, and you'll be not the same at all. But then about 10 or 12 years ago now, a bunch of researchers, Charlie Bennett is the first person on the paper, Gilles Broussard, and some other people, it's a long number of people, figured out that actually you could teleport things from one place to another. And the secret, if you can imagine this, is to make sure that your measurement actually reveals no information about the system you're trying to teleport. Instead, what you do is you set up this kind of funky quantum correlation called entanglement, where you have two entangled systems over here, an entangled system over here, and an entangled system over there. Entanglement is a form of correlation. Correlation just means two things get information about each other. In quantum mechanics, things can have more information about each other than they have any right to have. That's entanglement. You set up two of these systems that have more information than they have any right to have. You make a measurement over here along the system that you want to teleport together with this half of the entangled stuff. And that information reveals no evidence, no information about what the system was. It doesn't indicate it was Captain Kirk or Q or Dr. Spock. But when you send it over there, that information is enough to transform the other entangled stuff back into Kirk. So in fact, these are, it was a remarkable and shocking result, because I think that anybody who knew about quantum mechanics said you can't possibly teleport things. But in fact, it turned out to be possible in not only in principle, but actually in practice, because now a number of teleportation experiments have actually been performed.
What did they actually teleport?
Not me. Well, the people have teleported photons typically, like individual photon polarizations. And may I say, they don't do it with very high fidelity. Like if you had your favorite photon, I wouldn't recommend handing it over to these people.
So one photon, that's a long way from a Captain Kirk.
Maybe 7 or 8 photons. Now we're also trying to teleport. At the moment, we have an experiment to try to teleport one rubidium atom from one place to another.
Okay. And how far can you teleport?
Well, you can do it for many meters. Actually, in fact, since you can distribute entanglement over long distances, kilometers or more, there's no reason why you shouldn't be able to teleport things over very long distances. But again, I wouldn't volunteer to be the first person to do it.
You're very wise. Dr. Susskind.
Well, okay. The word teleportation is a rather charged word, and I think maybe it's less than meets the eye. Teleportation does not involve exceeding the speed of light. It does not involve moving things from one place to another place with faster than the speed of light. In fact, as far as I can tell logically, at a logical level, there's no difference between teleportation and just moving a thing from one place. moving a thing from one place to another. And that's not surprising that you can move some information from one place to another. I don't see the big difference.
So then what's the big deal? The
big deal, I think, is that you can do it for very microscopic systems, and maybe that you can send them with the speed of light, but not much less, but not faster than the speed of light.
Well, I can do that with a radio wave. We're broadcasting this program. It's a lot of information.
I would have to disagree with that slightly, Leonard, in the sense that first of all, what you say is correct, right? At bottom, teleportation is getting
but
from
then you
here
shouldn't
to there.
disagree with it.
But on the surface of it, it's actually incorrect. And if you go to a deeper level, like the superstring level, it seems to be incorrect as well.
Well, here's is what was considered a big deal at the time when it was found. These things called quantum states are parameterized by real numbers. So that means, maybe in a way that Seth would describe it, it takes an infinite amount of information to specify a quantum state. And in this teleportation process, when one performs the measurement that he was talking about that reveals no details about the system that's being teleported, what he meant by that was it reveals no information about the real numbers that are required to specify it. And so it was found that by performing a measurement that revealed 2 bits of information, you could get this quantum state that's parameterized by an infinite amount of information.
Yeah, so what I
from
say
one place to another.
What I say is weird is that the information you send from one place to another, if you just look at that information, it wouldn't tell you anything at all of what's being teleported. And yet you can combine it with this other half of this entangled state at the far end and use it to recreate the original thing in its entirety. So it's a rather strange situation in that you're not actually sending, at no point are you actually sending information which on its own allows you to recreate this thing. So, but I mean, the purpose at the end, for successful teleportation, right, is to get the thing from here to there.
Mm-hmm. Which you can do in other ways.
Yeah.
But there's another thing which is very interesting, which has to do with quantum information, which is worth talking about also. It has to do with duplicating information. You can take a page of information, here's a page in front of me that has some information on it, and I can faithfully reproduce it on a Xerox machine. At least I think I can faithfully reproduce it on a Xerox machine, but it's only classical information. In quantum mechanics, it's very interesting that you cannot clone information. You cannot take a thing and faithfully reproduce 2 versions of it simultaneously. This is one of the most interesting things about quantum information, the impossibility of duplicating an object. That I think you will find will not get undone by some clever experimenter.
No.
Okay, let's bring this home with what we can do with this information, with our understanding of information as quantum bits, as teleportation, as how we can move it from here to there. What are we going to get out of this? You mentioned quantum computers, and what is there any way that we can come out of the theoretical and into the practical with this?
Well, I think, okay, so the way I came to start thinking about the universe as a computer was I was taking little pieces of the universe, collections of atoms, and figuring out how to make them compute. And then I said to myself, well, what's going on here? They're actually computing already. All we're doing in the laboratory is hacking into this computation to make them compute in a way that's different. And here I actually have to take a exception to something you said before about our inability to program the universe. You made a metaphor where the laws of physics are the program for the computer. And well, I think that we're physicists here. Actually, I'm now a mechanical engineer, but I'm trained as a physicist. So we tend to be physics-centric. But it's not just the laws of physics; it's also the laws of chemistry and the laws of biology. And then when you started looking at all these laws, it's basically the program is any bit of information that can make a difference about how the universe behaves. And it's not so strange to think of, for instance, programming a biological system. In fact, genetics does it. That's what sex is about, right? Sex is about creating newly programmed biological systems. And I don't think you'd object to that form of programming the universe, would you?
I'm almost 68 years old.
Time for a new program, yes. No, I just want to answer now generally, just what do you see as we're in the information age. What's the future of the information age? Dr. Fuchs?
What's the future of the information age? I think Tony should take that question.
Well, I could talk a little, I think, about what one could do with specifically our understanding of information in quantum mechanical context, because I think that for many, many years, it was a sort of standard belief in the physics community that the weird phenomena which we associate with quantum mechanics were forever going to be confined to the level of single atoms or pairs of atoms and so on and so forth. However, in recent years, and particularly in the last 8 or 9 years, we've really gone very far beyond that. Seth was describing some of the experiments he's involved in where you actually see interference between these states of a reasonably macroscopic, that is everyday level, ring in which billions of electrons are circulating one way or the other. Many people ahead of time said that was simply impossible, it couldn't be done. It has been done now, and I think therefore we should be a lot more sanguine about the prospects of being able to observe these very subtle quantum effects in other systems where previously it was thought totally impossible. For example, certain types of biological system. I think it's at least on the cards that within the next few decades we will, for example, be able to see interference between the different conformational states of the rhodopsin, which is the first stage of human vision, and so forth. So I think that's one direction these people should go.
Tony, I'm just curious. Suppose it turns out that I'm not sure what you think one way or the other, but supposing it does turn out that quantum mechanics does fail for these large systems, do you think that means that quantum computers, large-scale quantum computers, are impossible?
I think that would very much depend on how exactly it failed. If it were to, I should say instead, it is perhaps a mildly amusing matter of history, that when I and a few other people started thinking seriously 25 years ago about the possibility of seeing the kind of interference effects which Seth is now seeing, at least one of my motivations at least, was precisely the hope that we might not see them. But, in other words, we would find that by the time we got to this kind of level, quantum mechanics has failed. Well, disappointingly, it hasn't, and that's conceivable. That's because in some sense, the systems we're looking at, very sophisticated as they may be from an engineering point of view and so forth, from a conceptual point of view, in some sense, is still rather crude. In the sense that you've got all your electrons are basically locked together. They're described by a single variable, and you're just interfering different values of that variable. There are lots much more sophisticated kinds of interference experiment we could do in principle. And if, for example, it turned out that in technical terms, a very highly entangled state automatically generated a failure of quantum mechanics, I think that could be the death knell for quantum computing. But certainly, as Dr. Susskind has said, there's absolutely no evidence right now that that's going to happen.
Well, this is something of a joke, but I think it's relevant to this. It likely depends upon, if there is a deviation from quantum mechanics, this issue of whether you can build a quantum computer is likely dependent upon what the deviation looks like. One of the crucial things in the technological development of quantum computation is to be able to do error correction. And for this, error correcting codes have been developed. I think I first heard this from Michael Nielsen, who's in the audience, but he speculated that if quantum mechanics fails, then perhaps we could just error correct that problem away.
That's funny.
Do quantum computation
That's funny
anyway.
because you error correct by making the system even bigger.
Even bigger.
Yep, that's right.
And you might expect that would make it even worse.
It might or it might not. I think it depends upon what this deviation looks like. If the deviation makes it look like, well, it would get technical here, but I could say things about trace preserving.
There's a very beautiful example that was very recently discovered in biology. It had been speculated for more than 80 years that photosynthesis might involve quantum coherence on a large scale. And photosynthetic molecules, they're huge. They have thousands and thousands of atoms, and they involve, a photon comes in, it gets absorbed. Actually, it gets absorbed not in one place in this molecule, but in a quantum superposition of many places. And now there's strong experimental evidence that actually this quantum coherence between all of these thousands of atoms in these photosynthetic centers is actually responsible for transferring that energy from where the photon is absorbed to where it can be turned into chemical energy. All the more remarkable because this is the sort of process where up till now we've only seen it at a few thousandths of a degree above absolute zero, and these are processes that are taking place at room temperature.
It always astounds me how you physicists, if you have a problem you don't understand it, you just add something to make it work. You add another dimension.
We call that BS. That's what we call it.
Yeah. In other words, we don't know.
That was the end of Dispatch C. This was by the Perimeter Institute in Canada, and also the host of Quirks and Quarks. or quarks and quirks, not sure which. We will continue with the third and final part to this momentarily.